All right, class, let's go ahead and get started. We're going to do a quick review of regression analysis, and then we're going to get on to multiple regression tonight, which is just a continuation of regression analysis that we did last week with a few little tools added to our repertoire. I want to start with a quick review. If you have your textbook, please turn to page 425. One thing we didn't do at the end that I had planned on doing last time was looking at the full computer printout of some sort of regression and thinking about how that related to all the terms we learned in class last week. So go ahead and turn to page 425. We'll take a look at a Excel regression printout, and that should take us through pretty much everything we did last week. So if you look at the top, we've got regression statistics in that box. It's got the multiple R, R squared, adjusted R squared, standard error, and observations. So let's start with the R square. That was a number that we used a lot last week. Can someone refresh us? Tell us what the R square represents.
How close to the line my points are, like the representation from 0 to 1, how perfect my representation is.
Close. I don't like the way you say how close the points are to your line. I think that's a good definition of the next one, which is the standard error. So let's stay with R squared, but I like how you said it, how good of a representation. So this was some sort of regression. In the example in the textbook, it looked at how many linking sites an app developer had. So this person who was developing apps wanted to know how many downloads they could get on their app, and they would potentially be able to predict that based on the number of websites they were linked to. So how much does each additional website, how much does being linked to each one additional website increase the number of downloads? And it gave us some information about that. Actually, I guess before we even get to the R squared, let's think about the equation for this line. So this app developer went to a business student such as yourself and said, can you please build me a regression line which is going to tell me how many downloads I can predict based on how many websites I link my app to. And you came up with this regression equation, this regression printout, and you came up with an intercept for this predicted value of 440, and you came up with a slope of 11. So what do those two numbers mean? Yeah, so that was the line of best fit. So the computer, Excel, calculated the line of best fit, which we did a little bit by hand and a little bit with Excel last week, but this just, boom, just put it in, it spit it right out.
So that's a relationship between my dependent variable and my independent variable.
Yes. And in this case, the independent variable is the linking websites. So you tell the app developer, or the app developer tells you how many websites his app is linked to, and then you can turn around and say, well, I can tell you how many downloads I expect. And I guess if you can look at the equation, you can see you might write it as, let me do this on the side of the board here. It's always tough trying to use the screen and the whiteboard at the same time. So I might say, in this case, the predicted value of y, which would be number of downloads, equals, what was it, 440? 440 plus 11x.
Yeah.
Right? So where x equals the number of sites. So if this app developer is hooked up to 10 sites, how many downloads would you expect that developer to, or how many times would you expect the app to be downloaded? X equals 10. Websites equals 10. Downloads equals what?
550.
Yeah, 550. Downloads equals 550. All right, so that's our estimate. But there, estimate contains some standard deviation, contains some guesses based on this line of best fit, also based on how confident we are with this intercept and how confident we are with this slope. And then we've got this printout to give us some of that information. So now that we've got the basics, let's get back to our printout and let's think about what these numbers mean. Let's go back to r squared. What does r squared represent? Amanda?
It's the ratio of the explained variation to the total variation.
Yes. All right, so how much of the variation can we explain with our regression line? And if it's a high number, then that's a high predicted value. And in the multiple r, that is just the r, which is the square root of r, which, hey, how you doing? Which is also a measure of goodness of fit. Like how accurately does this equation predict websites? And the thing about r is it can be positive or negative. R squared, because it's a squared number, cannot be positive or negative. It has to be between 0 and 1. But the r can be positive and can be negative. So what would it mean if we had an r that was negative?
There's an error.
No, that's not.
That's r squared. Sorry. I gave you a tricky quiz problem, but nice. Oh, you mean Nadia? Sorry.
If it's negative, then there's a negative correlation between
Exactly. So more websites might mean fewer downloads if the R was negative, or if this slope is negative at the same time. All right, standard error. Now there are three sort of standard deviation, standard error type of metrics in this printout, and we want to be very clear before we move forward that we understand them. Otherwise, we will slowly go insane as we try to jumble them. So let's just be clear about these three. The first one is the standard error, and the other two are the standard error to the right of the intercept and the linking websites. Let's start with the first one at the top. That's standard error. Does anyone remember what that is? Carlos?
That is the coefficient, or that is the value determined by the difference between the explained error.
Remember how you started with how close to the points are my line, and I said I like that?
So that's the distance between the points and the line.
Okay, so we created a line of best fit, and this gave us a standard deviation term for how close those points are to the line. That's that top standard error, and we call it standard error of the estimate. Now, let's jump to the other two standard errors. There's a standard error for the intercept and a standard error for the slope. What's going on with those two? Well, the standard error for the intercept and the slope tells us how confident we are with these two numbers. This 440 being the intercept, this 11 being the slope. So you can see with the 11, a slope of 11 has a standard error of 5.2. So it's about 2 standard deviations above 0. You recall that we had a big important question about, is this 11 significant, or is it just an approximation of 0? Is the relationship just 0, or is it something much more significant? So that gives us a ballpark figure of how many standard deviations it is above 0, and we can do more precise calculations with that 5.2. Similarly, with the 190, this is a standard deviation of the intercept slope, and that tells us sort of how confident we are with that number. Okay, so we've got r squared, percent of variation explained. We've got the multiple r, which is just the r, the square root. which is also goodness of fit measure, can be positive or negative. We've got the standard error at the top, which is the standard deviation from that line of best fit, and then jumping to the standard error of the intercept and the linking sites, which is the intercept and the slope. That tells us how confident we are with these two numbers. Now, let's take a look at those numbers in the middle there, the regression SS and residual SS. That's 60,500, 27,000, 87,500 number. What are those numbers? Amanda, yes.
One's the SSE, one's the SSR.
Yes. Which one's the SSE?
SSE is total? No, SSE is...
It's the explained, and it is the residual. So the first one is the SSR. That's the error explained by the regression line. The second one, the residual, is the SSE. So the unexplained error. And sometimes that's called residual, like the leftover after what you explain with the regression line, what's residual that is unexplained. And you add those both together, we get the total, 87,500. And that's sum of squares, all right? Squared deviations. We don't care so much if it's positive or negative. We just take the differences, square them all, add them all together. Okay, so we know those numbers, and also those are key in calculating the R squared, which is key in calculating the R. We've gone over the intercept coefficient and the linking sites coefficient, and we know the standard error associated with each of those. Now next, how about that t-stat number? Well, that t-stat number gives us an idea of how significant the intercept and how significant the slope is. And a larger t-stat means it's a more extreme value on that t-distribution. And a more extreme value on that t-distribution means it's more likely to be different than 0. It's more likely to be statistically significant. So the larger t-stat value means more likely to be significant. And then conversely, we have p-value right to the right of that. And that's just the opposite. That tells us the same thing the t-stat tells us, but just in a different way. That tells us how extreme or how likely this intercept or slope is to happen just by chance. And a higher p-value means there's a higher possibility of it happening just by chance. A lower p-value means there's a strong possibility that this is statistically significant. So the high t-stat tells us high chance of significance. Similarly, a low p-value tells us high chance of significance. Make sense?
No.
The high t-stat tells us a large chance of statistical significance, and the low p-value similarly tells us a high chance of statistical significance. So an extreme t-stat, 4, 5, 7, all right, that's in the extreme corner of the t-distribution. That tells us that that event happening by simple chance is unlikely. So it's not by simple chance. It's that we have stumbled upon a useful relationship. A slope or an intercept that means something. Because there's such a small probability of getting a t-stat that large. And the p-value tells us what that probability is. If it's a really large t-stat, it's going to be a small percentage chance. So t-stat, p-value have that opposite relationship that we've talked about actually for a couple of classes now. We introduced this concept 2 weeks ago. Then, to the right of that, we have confidence intervals. This tells us, with 95% confidence, where we think the true intercept of this equation is, and with 95% confidence, where we think the true slope of this equation is. And the t-stat, p-value, confidence intervals, they're all just shades of the same thing. All right. Makes sense. Anyone have questions about that? Now would be a good time to ask if you have any questions about that. Just want to ruminate on it a little bit. I'm sure some of your classmates would appreciate questions too.
Yes,
Or-
yes.
Yes.
The residual SS, that's explained.
That is the unexplained. So that's the SSE. Other questions? All right, are you all feeling pretty good about this? Like, could you just cite back to me everything I told you about this page?
No.
No?
Yeah, honestly, Excel ones really killed me this week.
Excel ones, like time-consuming wise, or just confusing wise?
I can say a little bit of both. Just typing them in, like, it really killed me time-wise. What I was trying to do, let alone then trying to actually take it after doing what I refer to as Excel help.
Oh, okay. I'm sorry to hear that, but I hope at least you survived.
No, I got that far.
And if you need to run something like this in the future, you'll know how to apply what we learned in class to Excel.
So I think I just gotta ruminate on it a little bit. I think I got it just.
Okay, excellent. So let's move on then to multiple regression, which is just a matter of adding a few components. We're going to now connect a single dependent variable with multiple independent variables. We might say we want to predict how much money someone spends online, and we're going to consider multiple variables. We're going to consider how much time they spend online, we're going to consider their income, and we're going to consider their their amount of free time, whether they have a job or not. All right. Amount of time online, income, and whether or not they have a job. And we're going to put all of those into a similar type of equation. We are going to come up with an estimated regression equation, just like we did with simple linear regression. So we'll have a predicted value of how much money. Oh,
Is there any more?
yes. There are plenty more of these
Almost like
printouts. Oh, yeah, there we go. Dan Ryan, can you grab one for Phil?
Thank you.
All right, we're going to have an intercept. We're going to have slope coefficients, except this time we're going to have multiple slope coefficients. This x1 value might be how much time someone spends online. This x2 value might be how much free time someone has. Another x value might be whether or not this person has a job. We're going to find a line of best fit in a similar way we find for simple regression, except this time it's just going to be a little bit more complicated. In fact, we'll call it a plane of best fit. We might have various points, time spent online, how much income this person has, and we will do a similar plane of best fit, except we won't really even talk about the math other than to say that it's done the same way. It's done the same way we did it last week, except it's just more complicated. Now that we are familiar with Excel, boom. Put it in Excel, and it crunches all those numbers for us. And it spits out a regression equation. All right. Again, the least squares method is used to determine the best fitting plane. All right. Each of these coefficients estimates the effect of the independent variables on the dependent variable, given the other variables that have been included in the model. So when we look at multiple regression, we might say, now let's look at income, and let's look at how much that explains on top of how much time a person spends online. Similarly, when we look at how much time a person spends online, we'll say how much does that explain on top of the other values.
values. And when we do that, each individually, we'll say we're assuming that the other value is held constant. So one variable is held constant. How much more does 1 hour spent online equate to money spent online? How much more does an extra $1,000 of income equate to money spent online? Now, does everyone remember this concept that there's a difference, a distinction we need to remember between our actual guess of the predicted value and our estimate for the expected value? If we want to guess actually how much money someone spends online, I want to know exactly how much Carlos spends online, I'm going to need to run some calculations, get an intercept, get a slope for each of these variables I want to consider, and I'm going to need to factor in an error term, because Carlos is affected by things that no one else is affected by. He is unique, so there's going to be some margin of error there. If I want to just determine his expected expenditures online, then I can just use the regression equation that I calculate. I don't have to add in that error. But I just realize that there is some variation if I want the actual term. I just wanted to make sure we're clear on that. Let's look at an example. Let's jump right in. Think about how we would solve a problem with multiple regression. So suppose this website, collegesports.com, keeps individual and team statistics for a variety of college sports. Its college basketball statistics include such things as field goal percentage, three-point field goal percentage, free throws, offensive rebounds per game, defensive rebounds per game, steals, turnovers per game. The staff at the website are planning to use their data to build a regression model that would identify the most important variables for predicting the team's success. To get started, they've chosen a sample of 20 teams from last season. Data for the 20 teams is shown on the next slide. And to demonstrate, we're going to focus on two of these variables. We're going to focus on win-loss percentage and steal and turnovers per game. No. We're going to focus on field goal percentage, like how accurately this team shoots field goals. Like if they shoot 60%, every time they shoot the basket, they make it 60% of the time. And then the other variable we're going to look at are turnovers per game. How many times they give the ball away to the other team. Now, just think intuitively. One of those independent variables is probably going to have a positive relationship with whether or not the team wins, and one of those independent variables is probably going to have a negative relationship between whether or not the team wins. Someone take a guess for me? Which one has a positive relationship? Which one has a negative relationship? Lucas?
The field goal percentage is a positive relationship, and the turnover rate would be the negative relationship.
I would think so. So the higher percentage field goals, the more chance you have of winning, so we're probably going to have a coefficient that's positive with that. And then the turnovers per game, the more times you give the ball up, you accidentally pass to the wrong player, that's probably going to have a negative relationship. That's going to mean you're going to win fewer games. Okay, so we've got the data. We've got field goal percentage of 10 teams. We've got turnovers for 10 teams, and we've got the win-loss percentage for 10 teams. We are going to crunch this in Excel, and we are going to get a predicted value for win-loss equation. We're going to have some sort of intercept. We're going to have a slope for field goal percentage, and we're going to have a slope for turnovers per game. I crunched this in Excel, and this is what I came out with. Let's take a look at the numbers and just chew on it for a minute. Let me take a sip of coffee. All right, same thing we just went through with the textbook. R squared. What is R squared? Phil.
Tells you how much of the independent variable explains the dependent.
Yeah, how much this regression equation explains in terms of variation. And we're at 52%, so not great, but we've got that. We've got a standard error term. we've got coefficients. This negative 50 for the intercept, this 3.6 for the field goal percentage, turnovers per game, we've got negative 4. So, and we've got some error terms associated with that. We've got some t-sats, p-values. We've got some confidence intervals associated with those. And then we've got our sum of squares for the regression, sum of squares for the error, sum of squares total. So let's look at these coefficients and think about what regression equation we are going to write based on this data. So we have a summer internship or just got hired from, with this company, collegesports.com, and they said, give us a predicting regression equation for how much a team's win-loss percentage would be. What would be the equation you would write? Randy, is that a hand or no? Go for it.
It would be 8.61 plus
What's the
negative
okay?
negative 4.7.
Okay. So I need some x. I want an x1. I want you to say x1, and I want you to say x2. And x1 means field goal percentage. x2 is going to be turnovers per game, and that's the amount you're going to plug in. And then you're going to spit out a y variable, which is the dependent variable, which is going to be win-loss percentage. So I want to hear y, I want to hear x1, I want to hear x2, and I want to hear all three of these numbers. And then I'll give you and also an equal sign in there. And then either a plus or a minus. 2 pluses or 2 minuses. I think I've given you everything that I want to hear in this answer. You just put them all together.
That's one. That's one would be the 3.61 field goal.
Yes. Okay, it would be close to it, but let's all right, I've thrown a lot at Randy. Someone else want to help him out? Phil.
Y equals 3.60 x1 plus minus 4.07 x2 minus 15.47.
Yes.
Or
we could put the minus 50 first. Let's see, do I have this? All right. Win-loss percentage, which is our y, equals negative 50 plus 3.61 times our field goal percentage minus, so plus and negative, which would be not minus, turnovers per game. So boom, we've got our multiple regression equation based on this Excel sheet we worked with. All right, interpreting the parameters. All right, this slope of 1. Each additional point in field goal percentage can be associated with a 3.6% increase in win-loss. Turnovers held constant. So, for every increase in percentage of field goal success, so Team A shoots 62%, Team B shoots 63%. Based just on that, I would expect Team B to have an additional 3.6% win-loss rate. Similarly, Team A has 10 turnovers per game. Team C has 11 turnovers per game. I would expect Team C to have a slightly lower win-loss percentage. In fact, I would expect Team C to have a 4.069% lower win-loss percentage. Make sense? Okay. Just like we had a standard error of the estimate last time, we have a standard error of the estimate this time. This is, as Carlos explained, standard error of the estimate is that variation around the line of best fit. Do not confuse that with the standard error of our intercept and our slope. That's something else. And last time we calculated the, this is the sum of squares error divided by, last time we said n minus 2. And this time we're going to add a component to it, which would still give us n minus 2 for a simple regression, but would give us something else for a multiple regression. We're going to divide that by n minus k minus 1, where k is the number of independent variables. So if we have one independent variable, then n minus 1 would be n minus 2, which is exactly what we did last week. If we have two independent variables, n minus 2 minus 1, which is n minus 3. We have 6 independent variables, n minus 6 minus 1, n minus 7. Same thing we did last week, just with a new little twist. Okay. Standard deviation figure for our best fitting line. Just like last week, we've got r squared, and we've got r. So r squared is the amount of variation that we explain divided by the amount of variation in total. And if that is high, then that is going to be a important, relevant regression equation with strong predictive value. Just like last week, r is the same. We take the square root of that, which also gives us a measure of best fit. Higher is better. And the beauty of r is it can be positive or negative. We can say it's a positive or negative relationship. We don't get so concerned with that in multiple regression because we do have multiple independent variables. Some could be positive, some could be negative. Essentially, r squared is the same as last week. R is also the same as last week. We're going to introduce a new term, which is called adjusted r squared. And this tells us, or this is a way of quantifying how we add additional variables into our equation. And statisticians have come up with the adjusted r squared to then decrease the predictive value of a regression equation as you add more and more independent variables. It's just a term that they've come up with to essentially punish the person who just adds more and more independent variables. Say, all right, I'm going to predict win-loss percentage with 37 different independent variables. I'm going to say steals, turnovers, at home, not at home, all this stuff. I'm going to put in as much as I possibly can. The more you do that, the lower your adjusted r squared will be. And someone looking at your model will say, oh, well, that person may have a high predictive value, but the adjusted r squared is fairly low. So that tells us they used a lot of variables. And it might just be a complicated formula. It might just mean that they didn't really think about what are the true predictive values of winning and losing a game, that they just threw everything, including the kitchen sink, into this. So adjusted r squared is a figure based on some math, which just penalizes the analyst for adding more and more variables. And I just want to keep that equation handy. If you need to do it for the homework, just crank it out. All right. Now, I'm going to introduce something that is going to be useful to us in determining whether or not a multiple regression has statistical significance. And it's called the F distribution. I'm going to go back a few slides and I'm going to explain how we can calculate it based on the Excel printout. And it's the new material for tonight, and essentially what it's going to tell us is when we're looking at more than one independent variable, we can't use the t distribution as effectively as we used for simple regression. We need to use something else called the F distribution. And let me go back a few slides and explain what it is. So let's look at this. This is the printout for the college sports example. We said, let's look at field goal percentage and let's look at turnovers per game. Recall, we have a sum of squares that are explained by our regression, sum of squares error, sum of squares total. Now, our sum of squares that are so let's start this way. So we have a total variation in this regression event of 5,000. We'll say that 2,600 of that can be explained with the regression equation. 2,400 roughly of that cannot be explained with the regression equation. So what the F distribution does is that it compares those two. It takes the amount explained divided by the amount unexplained. And if those are roughly the same, then it says, well, those are roughly the same. It's like you've got the same amount explained, same amount unexplained. I don't think you have a useful regression equation. If, however, you have so much more explained than you have unexplained, that the ratio is really, really high, then the F distribution says, all right, that was hard to have happened just by chance. It must be that you have stumbled on a useful predictive equation. So essentially, for the F distribution, we're going to take the ratio of the explained variation over the unexplained variation. And if that ratio is high, we're going to say we've got something useful. If that ratio is close to 1, then we're going to say we don't have something useful. Now the numbers get a little bit tricky from here, so I want to make sure you understand that that's the basic intuition. Ratio of the sum of squares R over sum of squares error. If that's high, we have a predictive value. If that's low, around 1, no useful relationship. Now, in terms of the math, we're not going to actually divide the SSR by the SSE. We're going to divide what's called the mean sum of squares residual and the mean sum of squares error, which is something in the next column. So to get the mean sum of squares regression, we divide the sum of squares regression, some SSR, by the number of independent variables. So if we have 2 independent variables, say field goal percentage, turnovers per game, we're going to say, all right, well, let's divide by the number of independent variables, and we'll say that the sum of squares we could attribute to each one would be that divided by the total number. So in this case, we're going to divide the SSR by 2, and we're going to get 1,300. For the SSE, we're going to divide that roughly by the sample size. And we're going to say, well, for each individual sample, here's how much error we can attribute to each one of those points. And then we're going to remember what we did. We're going to say, remember we divided this by 2, remember we divided this by n minus, n minus some other stuff, roughly divided by n. We're going to have a numerator and denominator degree of freedom. We're going to look on the F distribution, and we're going to see if that's statistically significant. Make sense? Okay, so basically what we're doing is dividing this SSR by the SSE. That's essentially what we're doing at its core. And we're saying, is this SSE so much more significant than, is this SSR so much greater, so much more significant than the SSE? That's essentially what we're doing. But the math to doing that is we actually divide the mean SSR and the mean SSE by each other. And to get the mean SSR, we divide the SSR by 2. And to get the mean SSE, we divide the SSE by roughly n, sample size, with I think the number of independent variables mixed in there. Okay. So let's go to where we can explain that a little more in-depthly on the let me skip ahead here. Okay. Yeah, I skipped ahead to slide 20 because I don't want to get lost in the intuition before we or you can circle the actual numbers. So, as I mentioned, this mean square regression is the SSR divided by K, which is the number of independent variables. In our example with the printout, it was 2 independent variables, field goal percentage, turnovers per game. So we just divided the sum of squares regression by 2. We got the mean square regression. Remember I said to get the mean square error, we divide the sum of squares error roughly by the sample size. But in actuality, sample size minus K, which is number of independent variables, minus 1. And then we put those two together on the next slide, and we get our F statistic. When we calculate that S statistic, we remember what we did to get the mean square residual and the mean square error, mean square regression and mean square error. We remembered how many independent variables, how big the sample size was. We remember that because that's going to be important when we open up the F table. And we consider that when we consider how large this number is. And in general, a larger number for this S stat, F stat, is going to mean, gosh, there's so much variation in this regression compared to the smaller amount we were able to create when we found the error in our best fit line. So we've got a meaningful, useful relationship. That's that intuition. All right, so let's go back and fill in some of the blanks here. Where do we leave off? So if 2 samples are selected from the same normal population, or from 2 populations having the same variance, the F distribution of probability of the 2 sample variances. So the question is, are they the same? Is the mean squares regression from the same population as the mean square error? If they are, then they're going to be roughly the same. If they're significantly different, then we've got a useful relationship. It's not symmetric, as you can see, because variances cannot be negative. So it's essentially a normal distribution, just like our Z table and just like our T table, except it just looks a little weird because we can't have negative values when we compare the variance from the SSR to the variance from the SSE. And remember, we need to make note of the degrees of freedom that we use when we pull those numbers. And we have 2 different varieties of the F distribution in the back of our book. One is for a 5% significance level, and the other is for a 1% significance level. And the questions on this will be, are we confident this multiple regression gave us something useful at the 5% level? Are we confident this multiple regression gave us something useful at the 1% level? So it says 5%, we go to the 5%. It says 1%, we go to the 1%. Okay, we will use what we now know about the F distribution to do a hypothesis test. And we'll create a null hypothesis that the slope of any one coefficient on this multiple regression is 0. In fact, all of them are equal to 0. We'll say I'm just going to assume that field goal percentage has nothing to do with win-loss record. I'm also going to assume that turnovers per game has nothing to do with win-loss percentage. That is my null hypothesis. And if when I calculate that F distribution, I have overwhelming evidence to the opposite, I'm going to reject that and say the alternative hypothesis is true. There is a useful relationship there. We looked at how to do this with t-tests last week in simple regression, and we did this with t-tests 2 weeks ago with just our first introduction to hypothesis testing. Now, we're going to use this with the F distribution that I just described. Okay, so can we conduct the F test? once the line of best fit, we compute the SSR, compute the SSE. All right, we had the SSR and the SSE printed out, and then we divide those. We don't need to explain this. This is just a reminder, unexplained versus explained. We compute the SSR, compute the SSE, and we're going to divide those by the appropriate number. For the SSR, to get the mean square residual, we divide by k, which is the number of independent values. Mean square error, we divide by n minus k minus 1, which is roughly the number of samples we have. And that's going to give us our S-step, F-step. And when we look that up on the table, we're going to remember what we did. Remember the number of numerators, number in our numerator, number in our denominator. Let's actually, let's crack open the book and do a couple quick examples of that. So let's turn to the beginning of chapter 12. Let's do, I think, number 2 and 4 are just very basic. Let's use the F distribution. Okay, so let's look at page 2, or number 2 on page 444. 444, number 2. So we're going to use the F table to determine the point beyond which you would find 1% of the values if the numerator degrees of freedom are 4 and the denominator degrees of freedom are 15. All right, so the numerator degrees of freedom 4, suppose we have 4 independent values, or excuse me, 4 independent variables. And then the denominator, we have maybe a sample size, I guess, of 19 minus 4 minus 1 would give us degrees of freedom of 15. We just remember 4 degrees of freedom in the numerator, 15 degrees in the denominator, and we want to know the likelihood of finding 1% of the values. So let's keep our thumb there on page 444, and let's flip to the back of the book to our F distribution. The first one is on page 571. That's the 5% probability. But we don't want the 5% probability, we want the 1% probability. So let's turn to page 572. And let's look at the degrees of freedom in the numerator is on the top row, goes 1 through 9. And remember, we're looking for degrees of freedom on the numerator at 4. So we go across to 4, and then we go down degrees of freedom in the denominator to 15, and we get 4.89. So what that means is, if we were to divide the mean square regression by the mean square error, and if we were to get a number greater than 4.89, we would say that is statistically significant. The chances of that happening by chance, 1%. So that is so unlikely. We're going to say it didn't happen by chance. It happened because we found a useful relationship. Okay, let's try the next one, 2b. 5% of the values, if the numerator degrees of freedom are 6, and the denominator degrees of freedom are 27. So you're going to use the other F distribution, the one on page 571. You're going to look at degrees of freedom in the numerator of 6, degrees of freedom in the denominator 27. So go ahead and do that for me. Sounds right. I heard somebody say what sounded like the right answer. Everybody go ahead and see if you can calculate that. This is, I know it's annoying, we have a new thing to learn, but it's nothing to be intimidated by, so let's just take a minute and get comfortable with it. Alright, who's got the answer to 2b for me? 2.459. Does everyone get that? All right. So what that means is if we calculate that F ratio and it is greater than 2.459, and we're satisfied we've got something useful. Same concept as a T stat, same concept as a Z stat. The greater that statistic is, the more likely we believe we've got something useful. Diane?
And just to clarify, so if the F stat is greater than that, then we reject.
Yes.
Okay.
Yes. We have overwhelming evidence to reject the null hypothesis. Okay. Now, let's see. We have a high F stat, as Diana pointed out, is going to conclude that we reject a null hypothesis. P-value works the same way in somewhat of an opposite fashion. A high F stat means a low or high p-value. High F stat means low or high p-value. Low p-value. Exactly. Exactly. And it is the same information. Low p-value means that is so unlikely to happen by chance that you would have a mean square residual that high compared to a low mean square error. That means you must have found something that, you must have found two populations where you have different variation, meaning in your world where you created this regression equation, you have less variation, which means you have strong predictive value. Okay, rocking and rolling on the F stat. Remember degrees of freedom. We have the printout SSR. We have the printout with our SSE, sum of squares regression, sum of squares error. We divide the SSR by K, which is number of independent values. We get the mean square regression. Divide SSE by N minus 1 minus K. We get the mean square error. All right. So SSR represents the variation that we can explain. SSE represents the estimate of the variation we can explain. All right, and we hope that this SSR is overwhelmingly larger than the SSE. Suggests that we have a large value for the F ratio is good. Connection between the t-test and f-test. In simple regression, they yield the same results, but we're introducing the F now because we need that as a tool to take the variation of all of these variables. Okay, so we can read over this F-test argument. It just essentially says the same thing I said a minute ago. If the F-test creates something significant, we say that the variation in the regression came from a different population than the variation that is explained, or unexplained, excuse me. Variation unexplained. So let me move on before I confuse you any further. All right, inference. So we're going to take what we know based on the F-test and what we know based on T-test, which we learned last week, and we're going to say, what can we infer? What can we say about these coefficients in terms of their predictive value? We're also going to look at confidence intervals, the exact same way we looked at confidence intervals in the past. We're going to have a point estimate for these coefficients, plus or minus a t-value, plus or minus the number of standard deviations. All right, significant and simple integration. F-test determines. Oh, okay, so this is the important point with the difference between the F-test and the T-test. The F-test determines whether or not the whole model. All right, we've got this whole model with field goal percentage and turnovers per game, and we do an F-test to see if there is value there. All right, if we've created variation that is different in what we can predict versus what we can't predict. The T-test we will continue to use for each of those values. We'll look at the t-value for field goal percentage, and the t-value for field goals per game, and say individually, what is the strength of those variables? What is the strength of each of those variables? Let's actually, I'm going to scroll back here to the Excel printout. Now that you have all the information, you need to look at this a little bit more, in a little bit more depth. So, wait a minute. Wrong way, sorry. I'll get there. Okay, this is our college sports example. Same thing we did a minute ago, or like an hour ago at this point. We constructed a predictive value for how many games a team would win, percentage-wise, based on field goal percentage, based on turnovers per game. We have a R squared, how much is explained. We have an R value. We have these three figures, SSR, sum of squares of the regression, sum of squares of the error, sum of squares of the total. All right, and we now know how to determine the mean square of the regression and the mean square of the error. The mean square of the regression is essentially the SSR divided by the number of independent variables. Mean square of the error is the SSE divided by essentially number of samples. And then to calculate the F statistic, we divide this one by this one. And 1332 divided by 139.7 gives us an F statistic of 9.5. So that, just eyeballing, we say, all right, that's a lot different than 1. So our first initial guess is there's some strong predictive value in this regression equation. And the significance of S is the p-value for F. So we could look in our chart to determine beyond which point do we say 9.5 is significant. We look at numerator degrees of freedoms, denominator degrees of freedoms, and I don't know what it would give us. It would give us like 3 point something. And we would say 9.5 is so much bigger than that. We're going to say, yes, this regression equation tells us something useful. Alternatively, the significance of F, which is just the p-value, tells us the same thing. There is a 0.0016 chance, which would be like 1/10 of 1% chance that this happened just randomly. So either 1/10 of 1%, you just randomly got lucky with these numbers, or alternatively, you constructed a model that gives us predictive value. So that's the F test. Similarly, we will still look at the t-stats for each of these individual values. We will look at the strength of the field goal percentage in measuring win-loss, and the strength of the turnovers per game for measuring win-loss. And we will still look at the t-stat and say, is that a strong t-stat? It's not bad. Is that a strong t-stat? It's a little on the edge. We'll have to crank the numbers to find out exactly how comfortable we are with it. P-value for t-stat gives us the same information as the t-stat, and then the confidence intervals, different shade of the same thing. Okay. All right, so you will be happy to know that you have all of what I would consider to be the taxing information in this class, in this particular class session. There's still some information I'm going to give you, but I feel like we got through the F-stat fairly successfully. I see some nods and some tired eyes, but I will continue and answer questions as necessary as always. Where are we? Okay, so F-test tells us the significance of the whole regression equation. T-test, each individual. So F-test results. I mentioned that our null hypothesis would not just be that one slope coefficient equals 0, but that they all equal 0. That is our null hypothesis when we do an F-test. Every single one of those coefficients equals 0. The coefficient for field goal percentage and the coefficient for turnovers per game, null hypothesis, all equal 0. The alternative is that at least one of them does not equal 0. And we calculate f-test that way, rejection based on the critical value or the p-value. Alright, we've done this same thing before. Alright, hypothesis testing. So for each of the individual, so we've got the f-test, which we can do a hypothesis test for. We've also got a t-test, which will look at each individual independent variable. I think for the, the field goal percentage, it was a coefficient of 3.6 or something like that, and we had a t-value. We can test the strength of that individually. We can say, what are the chances that that particular variable has predictive value? Similarly for the turnovers per game. We can say, what is the chances that that particular variable has value? And we will look at that the same way we did last week with our t-test, our hypothesis test with the t-test. The F distribution just comes into play when we try to look at everything all together. So we might calculate a t-stat. This could be the slope for the field goal percentage, slope for the for the turnovers per game, and this is our standard deviation of the sampling distribution of the sample slope. Thank you. Same rejection rules based on the critical value of t or based on the p-value of that stat. Individual tests. The proposition that independent variable brings no additional explanatory value. I mentioned this already. So if we're going to look at turnovers per game, we want to test that that brings significant increases in predictive value above and beyond what field goal percentages bring. And we look at it the other way around. We want to know that field goal percentages bring significant predictive value above and beyond what turnovers per game bring. Right. Okay, F-test, college sports, I feel like, yeah, let's, what do we got here? Both. So let's do this F-test for the college sports example. And I already alluded to this. I said the mean squares regression is 1,300 something. The mean squares error is 139. We go back to our Excel sheet. We divide those by each other. We get 9.5. We get a p-value of 0.0017. And I already went through the song and dance. I said there's a 1/10% chance that that happened by chance. Too unlikely. Let's reject the null hypothesis and say yes. This regression equation has some predictive value. Okay, so this is just those numbers categorized. SSR divided by 2 equals mean sum squares. SSE divided by 17 equals that. Okay, not only do we want to test the whole regression equation, but we want to test the two independent variables. The field goal percentage and the turnovers per game. And we test those, not with the F distribution, with the T distribution, just like we've done the past few weeks. And in this case, we look at each one, null hypothesis, slope of 0 for, say, the field goal percentage, and for the turnovers per game. Alternative hypothesis, the slope does not equal 0. Sorry, I don't know if that came out. That should be a not equal 0 on slide 33. Say we have a 5% significance. Degrees of freedom for our t-test. Remember for our t-test we used degrees of freedom n-2 last week? Okay, well, we're going to do the same thing this week, except we're going to call it n-k-1. So if we just have one independent variable, it's n-1 minus 1, n-2 like we did last week. But now that we're adding more independent variables, it could be a little different. If we have two independent variables, it's n minus k, which is 2 minus 1, and if we have 20 samples, 20 in our sample, 20 minus 2 minus 1 is 17. Let's do a quick check in the back of our book. Just make sure we don't forget how to look up critical values for t. Let's, at the 5% significance level, let's confirm that that critical value for the t-test is 2.11. So flip back to your t distribution, and let's see if see if you can find that critical value for 2.11. "17 degrees of freedom, 5% significance, which means we would have a 2.5 percentage in each tail. Right? Looks good. Looks good? Okay. So we flipped in the back of our book. We said the critical value for t is 2.11, and we're going to reject the hypothesis that the slope is equal to 0 if the absolute value is greater than the absolute value of 2.11, or if the p-value is less than 5%. Our test statistic for the field goal percentage per game, remember the coefficient for the slope is 3.6. We divide that by the standard deviation of the sampling distribution of the sample slope, and we get 2.6. We do the same thing with turnovers per game. Remember, it was a negative relationship, and we get negative 2.12. So I want 2 volunteers to just talk me through how we interpret this number, and then I want another volunteer to talk me through how we interpret that number. I've been talking for a while. I need a break. Somebody tell me what we do with this 2.16 that we've worked so hard to calculate. Yeah, why do we reject the null? It is greater than 2.1, and it is, in fact, so unlikely to have happened by pure chance, we're going to assume that we have constructed a useful, statistically significant relationship. All right, how about this one? It's negative 2.1. Same thing. We reject. The negative relationship is past our level of significance, where we say, that couldn't have happened just by chance. We have a useful relationship. But notice, though, it's really, really close. It's really, really close. Yeah, and that'll come up later when we look at the same thing, just in a different shade. So just make a mental note that this turnovers per game, we think there's a useful relationship, but it's really, really close. Yeah, you could say it's not strong. Yeah, you could say it's not strong. It meets the 5% threshold. It would not meet the 1% threshold. Okay. Let's do confidence intervals. And we're going to do confidence intervals because it's the exact same way we would approach it in past classes, and we're going to use the same nuances we just used with our t-critical value. Now, we're not doing confidence intervals with the f-test. That is just a one-off test we will use to determine the strength of the overall regression equation. But we're going to use confidence intervals with our t statistic, just like we have in the past. Remember, we're going to use n minus k minus 1 degrees of freedom. Last week we just said n minus 2. Now we know that that means something, n minus k minus 1, because we may need to subtract n more from n if we have more independent variables. All right, field goal percentage. For a 95% confidence interval with degrees of freedom equals 17, the t-value is 2.11, which we determined from last time. So we are going to take our point estimate of 3.6. We said this is the coefficient we came up with, and we said for every 1% increase in field goal percentage, meaning Team A shoots 74%, Team B shoots 75%, we expect Team B to win 3.6 percentage more games, or more in the win-loss calculation. We're not 100% sure of that, so we're going to take our confidence interval which is the appropriate 95% confidence interval from the t-stat. It's 2.11. And then this number, this 1.37, where did we get that? Where'd that come from? Standard deviation of the sampling distribution of the sample slope. All right, just how confident we were with that slope number. And then we come up with 0.699 to 6.5. Can someone tell me the intuition there? All right, just talk those numbers through and tell me what we interpret that to mean. I'll pause for a minute while I look at it. So I need someone to explain those two numbers. What does it mean? Layperson's term. How to impress your boss without confusing her. Very, very good. I want to hear though. I want to hear something about the slope or the relationship between the relationship as far as field goal percentages. Like this 3.6 represents our slope for field goal percentages as it relates to win-loss record. So for a 1% increase in field goal percentages, we expect a 3.6% increase in win-loss. But if we were talking, so maybe I would settle for just somebody explaining that in the same terms of 0.699. It could be that it's not 3.6. It could be that, what, Keith? All right, it could be that a 1% increase in field goal percentage leads to a 3.6% in win-loss record. But it could also be that a 0.699, that a 1% increase in field goal percentage leads to what? 0.699 increase in what?
Oh no.
Yes, yes, yes. It could mean that a 1% increase in field goal percentage leads to a 0.699% increase in win-loss. Same thing. It could be as high as 6. All right. If you increase your field goal percentage by 1, you may be able to increase your win-loss percentage by 6.5. All right. We know it's somewhere in between there with 95% confidence. Yes, Lynn?
Is K always 2?
No. K is the number of independent variables. Yeah. In this case, we have 2 independent variables: win-loss percentage, turnovers per game. We could have like 10. Last week we only had 1, so we didn't even need to introduce K. All right. Same thing here. Turnovers per game. We have our estimate for the slope coefficient is -4. So what that means is we think holding field goal percentage constant, we think for every 1 additional turnover per game a team has, their win-loss goes down by 4%. We're not 100% sure of that. We need a confidence interval. So let's take our confidence interval we're comfortable with at 95%, and 17 degrees of freedom is going to be 2.11. So let's plus or minus this 1.9 number. What's this 1.9 number? Yep. Standard deviation of the sampling distribution. Yes, of the sample slope of this other slope. These are 2 different slopes. And this one has that standard deviation. Okay. And what does it come out to? -8.11 to -0.22. Can someone talk me through the intuition of that? This is a little more rewarding.
That the slope of the turnover per game is between -8.115 to 0.022.
Yes, yes. All right. It could have as significant of an 8% influence on our win-loss record. All right. An additional 1 turnover per game could negatively impact our win-loss by as much as 8%. Or it could be that it only negatively impacts our win-loss percentage by 0.02. So this is in percentages. So this would be 20 hundredths. Yeah, I guess it would be 1/5. Yeah, so 1/5. And why I said this is rewarding is this is very, very close to 0. Remember how I mentioned earlier that this particular slope coefficient just barely met our standard when we did the t-test for it? So it just barely met our standard because the confidence interval brings it so close to 0. And if the confidence interval crosses 0, we have to include 0 in our 95% confidence. We have to say, well, it could be 0, it could be -8. If it includes 0, I have to say, well, it could be 0. I can't reject the fact that it's 0. Okay. All right, I think, so we've got qualitative variables, which are something we'll call dummy variables. And then we've got just some discussion on best practices with building a regression equation. We've just got those 2 things left. Why don't we take a break? Take a few minutes. Let's, all right, let's, it's 7:50 now. Why don't we come back at 8:02? Does that sound okay? 8:02? All right, I'll see you then.
Shooting.
Yeah, they're new. Yeah, yeah. Yeah, I look exactly like you. But then I realized I was dressed kind of spiffy. This guy was not. Yeah, yeah.
Just suck it up. Just suck it up. All right, I promised an 8:02 restart time. It's now 8:03, so I will restart and let the others filter in as they see fit. So we're going to talk now about. It's like I'm talking in class, but that's okay. I can do it. We're going to talk now about qualitative variables, also known as dummy variables. These are variables that cannot be measured in increments. They can only be measured as a whole. For example, in our college sports example, it might be, does the team have a mascot? Yes or no. We can't say the mascot is, 50% or 20%. It's just a yes or no. Another question might be, does this team have their own basketball arena? Yes or no. Yes, they have their own. No, they borrow from someone else's. So essentially what happens with this, it just becomes a lump sum predictive factor. It's like an additional intercept. So if the team has a mascot, then the win-loss percentage increases by 4.5%. If the team owns their own basketball arena, win-loss increases by 7%. Everything else is the same. So, please, welcome.
I didn't know you started. I was like,
Yeah, I thought that was weird, but I don't know.
yeah, well, we're sitting outside. I didn't know you were starting.
We are starting. Feel free to come or go as you please. All right, whatever helps. I'm here to help. All right.
Break is over.
Yes, it was over like 3 minutes ago. But so qualitative variables. Can someone from this half of the class explain what a qualitative variable is? Diana.
It can be measured in increments only as a whole.
Yes, can't be measured in increments only as a whole. For example, Justin.
We were talking about the sports. If you had a mascot, it may increase just by a drop, if at all.
It'll increase, or it might increase, it might decrease, but it'll just be a lump sum increase. You only have one mascot, or it's only a yes or no answer. So essentially, this will just be an additional intercept number. Like it'll increase or decrease based on whatever you find with the regression equation, but it won't matter if you have 2 mascots or 10 mascots, or you have a mascot that is partially whatever. It's just the one variable, yes or no. So, let's see. In effect, this results in 2 equations, 2 planes, one for each dummy variable. For example, let x1 be the dummy variable. And it's just, if we have a mascot, we would put a number in for that. If we don't have a mascot, we would put a 0 in for that x coefficient. All right, example. Let's look at housing. A number of important variables can influence the price of a house, including house size, lot size, number of bedrooms, number of bathrooms, the age, location. All right, so let's take a survey of Seattle, Washington's housing market. All right, let's look at how much this sample of 20 houses sold for. Let's look at the house size, and then let's look at the location. So we've got 20 samples. We've got selling price. We've got house size. And we've got zip code. Now you can see if you look closely that we only have 2 zip codes. So this zip code is going to be our dummy variable, our qualitative variable. It's either yes, we were in this zip code, or no, we were not in this zip code. And we're going to calculate how much more or less that makes the selling price. So we're going to get an estimated regression equation, call it the predicted value for y, the estimated sales price, times the intercept, b sub 0, times x1, which is the house size, times x2, which is, we'll put in a 1 if this is in a certain zip code, and we'll put in a 0 if it is not in the zip code. So if it's not in the zip code, we put a 0, and that just goes away. If it is in the zip code, we put a 1, and whatever number comes out, that's how much we add to the selling price. All right, I did a regression on this one, and the various numbers came out. We've got all this stuff, r squared, adjusted r squared, our standard error of the estimate. Let's take a look at these numbers here, this intercept, this house size coefficient, and the zip code coefficient. We've got the intercept of 97.9, we've got the house size of 0.185, and we've got the zip code of 218.9. So let's write this regression equation. Let's do that first. All right, so try writing it down. Just write it down on a piece of paper, and then we'll get back together in 30 seconds and see if we agree. All right, so we've got the selling price, which we're predicting. Let's call that y hat. Y hat, all right, equals. All right, we want some numbers that are going to predict the selling price. What are they? Selena? What's that? 97? 0.892, and that is, yeah, I like it, the intercept. What, Randy? Plus?
Yeah.
185 x sub 1, yes.
Plus 200.
Okay, is that it? Is that it?
Sorry, X2.
X2, fantastic. All right, so, and the X2, so what does this part tell us? How can we describe this part of the equation as it relates to the predicted value of a home? It's 218. And this is in thousands. Phil.
So I guess since X2 is a dummy variable, then it can only be 1 or 0. If it's 1, the house value will increase by 218.9. If it's 0, 0.
Exactly. All right, so houses in this zip code sell, on average, $218.9 thousand more.
What's the intercept?
Well, the intercept, yeah, the intercept is consistent whether it's in zip code 1 or zip code 2. If it's in the less expensive zip code, then this is a 0, so we just don't have 218,000 in that predicted value. Okay, and we've got the other stuff we talked about. We've got this, sum of squares SSR, SSE, SST, and then we've got this mean square regression, mean square residual. All right, somebody refresh us. What are those two? What do those two mean, or how do we get those two? Yeah, you know what? The intuition might be hard to explain at this point, but just tell me how they were calculated. Amanda.
SSR divided by 2.
Yep, SSR divided by the number of independent variables.
SSE divided by 6.
Yes, yes, yes. And this one on the top, this mean square regression, is the average variation that we're able, from the population that we're able to explain in this set of data. And then this SSE is the average variation in the population that we're not able to explain in this set of data. So able to explain, not explain. All right, if this is so much more than this, we're going to say we have something significant on the whole. So we divide this by this, and we get our F statistic of 8.4, which we're looking pretty good. All right, we know that's significantly more than 1. We'll need to look on the F-test on the F-test table to determine if that's good enough, based on what we did with the degrees of freedom here and degrees of freedom here. And we could also just look directly at the F significance, which is the p-value for F, which is 0.002. So that is 0.2%. Is that likely? It's very unlikely that this happened by chance. It's very unlikely. So we're going to conclude that we've got a significant relationship here. We were able to determine that this regression is just not blind luck producing values. And then this F-test tells us the whole regression equation. And then we look at the two individual values, and we measure the strength of each of those values based on our old reliable t-test. Okay, so we've got our predicted equation. We know what we might be looking at for the F-test. We know what we might be looking at for the t-test. We know the meaning of this qualitative/dummy variable. All right, so this is the equation. All right, this is the sum of squares stuff that we talked about. The F-stat. All right, interpreting the coefficients. So this square foot, we interpret that 0.185. Each additional square foot of area can be associated with a $185 increase in selling price. So 10 square feet more in your house versus your neighbor's house might mean an extra $1,800 in your selling price. Other things held constant. And we already talked about this, the second variable, the dummy variable. If you are all things equal in the more expensive zip code, your house might sell for an additional $218,989. Let's do our F-test. All right, let's take our mean square regression divided by our mean square error, and let's get 8.48. Let's look. Now you can see we've got the answer here. Reject the null hypothesis that this is not significant. But let's do a quick. Oh yeah. Right, we've got the F critical value of 3.59. But let's just confirm that. Let's look in the back of our textbook at the F table, and let's look at a 5% significance. And then let's make sure we've got our degrees of freedom where we want them. All right, so for the degrees of freedom in the numerator, the mean square regression, we have two independent variables. So degrees of freedom in the numerator is 2. For the degrees of freedom in the denominator, we have our sample size n minus k, which is 2, minus 1, which is going to give us 17. So we're looking in the F distribution, degrees of freedom numerator 2, degrees of freedom denominator 17. And we're looking at the 5% one, which would mean 2.5% in either tail. What are we talking about? 159. Okay. Like that. That would ruin our night, right? We'll just stop and rethink this whole thing. We know that since the 8.48 is more significant or larger, it's more extreme. Could be is more extreme than 3.5. We could reject. P-value tells us the exact same thing. Let's look at the individual. All right. So we know this whole regression equation as a whole has some value because the F-test tells us that. But let's look individually at the square footage and the zip code. So we take our point estimate from the square foot, we divide by the standard deviation of the sampling distribution of the sample slope, and we get a t-value of 3.426. If we were to look in our t table in the back of the book, we would say for a 95% confidence with degrees of freedom of n minus k minus 1, 17, we would get 2.11, just like we did in the last example. And we would say that this particular value is also significant. So we were saying two things. One, the regression equation as a whole is significant. Now we're looking at this predicting factor of square footage, and we're saying that that tells us something significant over and above what we get out of the zip code equation. Same thing. Let's look at the zip code. And let's see if this tells us something significant over and above what we get from the square footage. So we take our point estimate of 218,000, divide by the standard deviation of the sampling distribution of the sample slope. We get a t-stat of 3.3, and we know that it's past our t critical value of 2.11. And we have a low p-value, lower than 5% anyway. We reject the null hypothesis that this slope is 0, and we say we have a significant predictive value in this variable as well. Okay. So let's look now at some general questions about this multiple regression as a whole. Why not just conduct a series of simple regressions? Why not first do a regression of home selling, of square footage as it relates to home selling price? And why not do a simple regression of the various other factors? Why do them as a multiple regression? And then we'll talk about multicollinearity is the other really big thing we'll discuss. So multiple regression, I'm just going to read these each to you, and then we'll discuss them. Multi-regression allows us to identify the effect of one variable while controlling for the effect of the others. So it allows us to identify the effect of square footage while controlling for location. It allows us to identify the effect of increased field goal percentage while controlling for turnover percentage. If we didn't, then we really wouldn't know which variable was having more of an effect. We might say, well, the field goal percentage has some effect, but more of the effect is related to the turnovers per game. So let's just look at one at a time. And by putting them both in the regression equation together, we can look at one, the effect of one, with the other held constant. And by taking into account the likelihood of a shared or overlapping predictability, multiple regression can reduce the risk of assigning a greater degree of importance to a particular independent variable than is merited. So, if we look at field goal percentage and turnovers per game, if we put them both in the same regression equation, we can say, tell me field goal percentage predictability over and above what turnovers predicts. Vice versa. What turnovers predict over and above what field goal percentage predicts. So that's the rub. The bottom line on multiple regression, it allows us to isolate variables more effectively. Maybe if we're looking at a business opportunity, We might want to look at very specific variables in isolation. And so we put them all into a regression equation and say, well, this one, the others held constant, determines that we might make more sales. So let's look for markets where that is more of a factor. So, brief word on why we use multiple regression. The other obvious reason we use multiple regression is because it gives us more predictive value, right? And if we consider multiple variables to determine how much money someone spends online, then it may tell us more than just how much time, how much. It may tell us more if we look at more things. If we just look at how much time someone spends online, we may not get as much predictive value as we want. But we need to be careful about looking at a whole range of things without thinking about how much they contribute individually. The very last thing I'm going to discuss, in an advanced class you'll see more examples of this, and this will be a very important factor. But tonight we're just gonna talk about it for a minute. It's called multicollinearity. Multicollinearity. Let me see if I have a definition of that. Refers to correlation among independent variables. So, suppose I'm looking at predicting how much money someone spends online. Let's go back to that example. And I'm going to look at independent variables, how much time someone spends online, how much money someone had, or how much income someone makes, and how much free time someone has. Now suppose I discover that there's a strong relationship between how much income someone has and how much free time they have. So if they have very little income, they have a lot of free time. I discover that relationship. And I say, oh gosh, well, the people who have very little income, they're the ones that have so much free time. There's such a strong relationship between those two variables in my regression analysis. Those independent variables relate so strongly to each other that I can't tell which one is having more of an effect on the predictive value. Does that make sense? Let me give you another example. I heard this example when I was watching a YouTube video just to freshen up on the F test. The example is, suppose I'm having dinner and I want to salt my meal. I put a little bit of sea salt on my meal, and then I put a little bit of table salt on my meal. I can't tell which one of those made my meal more salty because I put both of them on my meal. They have such a similar effect on the salt taste on my meal because they interact, in this example, they interact with each other, they're related to each other. So that's just a brief note on multicollinearity. If two independent variables are highly correlated to each other, it makes it difficult to determine which one is having an effect on the predictive value. Yes?
Is this the term they also could be like interchanged with redundancy? Do they use that term in that?
It could be.
It's just redundant.
It could be redundant, but also it just makes it hard for us to strip out. Because they could both be important, but we need to account for that multicollinearity.
What about like the basketball situation, like turnovers and having the ball stolen from you?
Yeah.
Having the ball stolen from you would lead to a turnover, right? So would that be...
Okay, so steals, maybe we look at steals per game and turnovers per game. So if we're playing really aggressively where we're trying to steal balls from the other team, maybe that makes us tired when we're on offense, so we have more turnovers?
I just think if you steal the ball from the opposite team, it's a turnover.
But it's a turnover for them, though. It's not a turnover for you.
Right.
The person who retrieved the ball.
Yeah.
You
Yeah.
can define what a turnover is, so there's a lot of confusion
Sorry.
there.
Well, let's find it. All right, let's
Or
think of
just
something.
just in the game, say one basketball game as a whole, not focusing on one team or another. If that game had a high percentage of turnovers, and there's also one of the other variables was having the ball, how many times the ball was stolen on the court. They both mean the same thing.
I want to find an example
I know
of this,
it's
but
maybe not.
But I don't think that one works.
Maybe, like,
Let's find one that works.
Steals when the ball goes out of bounds because they're both considered turnovers.
What about
Okay.
like your? I think there's a statistic of your defensive score. So how well the team plays
How about-
defensively,
how about
and
this?
then blocks.
Yes. Okay. I like it. So blocks per game and steals per game. Okay. So I have a team that has a high number of blocks per game and a high number of steals per game. So those might be highly correlated with each
Right.
other. So if I put both of those in my regression equation, it's hard for me to tell which one is having the true effect. Because if I'm playing so aggressively where I block everyone's shot, that might be the predictive value. And steals are just blocks that
Right.
I happen to grab.
So they're like tests to determine which one's stronger.
Well, there's no real right way. You just need to think about what may be causing noise in your regression equation, your multiple regression equation, and which ones have the most predictive value for whatever you're trying to determine. I was a little disappointed actually that your textbook didn't go into any of the fun details of that. They just explain a little bit about multicollinearity, and then they give us the F test, which is very important. We need to understand that, and we need to know how we can use the T test based on the same way we've done in the past. But yeah, there's not necessarily a right way of approaching multiple regression. Great. Okay, so you survived multiple regression. You survived in the heat. All right, I'll see what I can do about this next week. Hopefully it'll be fixed. But I'll look forward to seeing you next week. Let me know if you have any questions.